So now I am in my 3D Revit model. The case study of focus is this 3-floor-story residential building with multiple apartments and a total surface of 1,700 meters square. I had already did the import of the model into ArchiWizard, so if I click in my second tab, you should see generated my ArchiWizard model. The plugin of ArchiWizard within Revit presents the same functionalities as the ones available in the autonomous version and is shown as follows. In the upper headband, you have diverse functionalities. First, the functionality to help you synchronize your ArchiWizard model with your Revit main model. Functionality is to handle your 3D view, to open and save your variants, to handle your environment, like masks, for example, or to add some exterior object like trees, for example, or to change your weather conditions or weather file. Parameters to help you configure the building information, such as zones, the scenarios, the wall composition, the glazed area composition, and the thermal bridges. Some bioclimatic tools that we are going to use, such as the solar imagery, and all the previously presented modules, including the DTS module for detailed simulation. A functionality that helps you display your results and to generate automatically reports, and the library containing a bunch of elements related to the building information like materials, wall composition, outside objects like trees, solar shading elements, etc. In the lower headband, all relevant real-time calculation information are shown, like comfort indicators and energy demand indicators. So once the model is launched, you had already chosen the type of the building used, and with that comes an already filled information about the heating set point temperature, the ventilation rate, the occupation, etc. So before getting into this case study, let us verify quickly the communication of ArchiWizard model with the Revit main model. So if I randomly choose a room and click on it, you should see displayed in the Revit properties all the information regarding this zone, including the name, the area, the level, etc. If we click on the relevant floor in Revit, 2D floor, you should see selected the right zone. So that means that the two models are linked and communicating. If I change, for example, the name of the room, you should see the updates automatically reported into the Revit properties. So now we need to understand first the condition of the building and its exposition in order to come up with effective bioclimatic strategies. Bearing in mind that we need to consider two types of comfort in our strategy, a winter thermal comfort and a summer thermal comfort. Each is contradictory because while summer comfort requires to minimize the solar irradiation through walls, the winter comfort requires to absorb as much heat as we can. The weather file used is the current conditions of Paris, so we are located in a temperate climate. This means a moderately cool winter with a generally cloudy sky and warm summer with a mean temperature of 25 degrees. So let us understand a bit the exposure of our building regarding the sun. And to do so, I'm going to use the solar path. So the solar path, or the day arc, refers to the daily and seasonal arc-like path that the sun appears to follow across the sky. The point here refers to the current position of the sun. The sun will change trajectory in different times during the year. So during summertime, in the northern hemisphere, the sun is up in the northeast and is set in the southwest, and is high in its position in the sky. So that means that the solar gain will mostly be absorbed through the roof and the east facade in the morning, but also the south facade around noon and a part of the afternoon when the irradiation levels are high. Since the position of the sun is high in the sky, the sun rays will hit the southern glazed area with an incident angle. So that means that if we want to protect our glazed area from the summer sun, horizontal sun shading solutions in the southern facade will be a good solution. In wintertime, February for example, the position of the sun is lower in the sky. The sun is up in the southeast and is set in the southwest. So that means that the southern facade is the most irradiated most of times. So let's now check the irradiation level to have more information. ArchiWizard includes a tool to run solar irradiation calculation on the building. The solar irradiation is simply the energy received in the building envelope during a period of time. I define this period in a year. So we confirm that now the roof receives more irradiation than the other facades, but also the southern facade compared to other ones. We notice that the upper floor receives more solar irradiation than the other floors because it is exposed to direct sunlight. So we are going to implement strategies to reduce the hours of discomfort. So for now, we focus on the whole building, but what I did is I created a zone only for the upper floor, and we're going to focus during this study on the upper floor only, and we can display its results in here in real time. So from the use of the sun path and the solar irradiation tools, the most exposed areas are the roof and the upper southern facade. Now I know that the roof is well insulated. I have put a thermal resistance of 8, so more insulation won't help. So I am going to act on the shading system in the upper southern facade. As talked about previously, there is a library in ArchiWizard that allow me to search through a lot of interesting components for the building simulations, like the envelope materials, certain HVAC equipment, solar shading elements, etc. To protect my building from the excess of heating through solar radiation, I can search through the library from different sun shading technologies so I could use one. This one, for example. To gain time, I had already prepared the sun shading design with a certain length of plates, and I am going to activate them. But before doing so, let us retain the results of hours of discomfort. It is about 887 hours, and the heating demand is about 22 kilowatt hour per meter square. So now I'm going to activate my sun shading system. So by activating them, I should see in real time in my calculations the change. So we gain a reduction by more than half of the number of hours of thermal discomfort, but we also raised about 2 kilowatt hour per meter square of heating demand. To check why we had 2 more kilowatt hour per meter square of additional heating, I am going to use projected shadow simulation. So in February, for example, as you could see, the shading covers approximately half of my glazed area in February 40th at 1 p.m. And that raised the heating demand. So what I will try to do is try an iteration with shorter shading blades to avoid additional shading during winter. So now as it is calculating, I should see in real time the results of my iteration. So now I deduce that this iteration has reduced the discomfort hours by 180 hours. It's not the same level of gain as it is in the first iteration, but at least I didn't raise my heating demand, as it stays the same. So the point now is to try new iteration to optimize the solar shaded length in order to reduce the thermal discomfort hours, but also to not raise the heating demand during winter. So in that way, we will find an optimal design that help us reduce the thermal discomfort hours without raising anymore the heating requirement during winter. So I found an optimum with medium length shading blades, and we are going to conclude in real time the results of this iteration. So if I chose this length of solar shading, I have successfully reduced 247 hours of thermal discomfort. We were about 800 hours, and now we are at 641 without any more raising the heating demand.